Hey guys, today we're going to be in chapter 5, section 3 of our textbook, which discusses frictional forces. Now, most of that's already familiar to you, so I'm going to talk through regular friction really quickly, and I'm probably not going to do a lot of the examples there because they're really similar to stuff that you should already know how to do. But we are going to get into terminal speed today, terminal velocity, and a little bit of fluid resistance. So that stuff's going to be new. That's going to be the calculus. We'll see it here in a minute. So first things first is to make sure that you know how friction works. The idea is that friction equals mu, that's coefficient of friction. I'll write that here, times Fn, that's the normal force from the surface. Now remember, the normal force always points perpendicular to your surface. So if you're on the ground, that's flat, points up. If you're on a slope, it points at an angle, but it's always perpendicular to your surface. Okay, I'm going to erase that stuff. Okay, and then your mu, the coefficient of friction, is based on the surface that is sliding across, okay? And it's actually dependent on both the surface and the object itself. Taking both of those factors into account is called the coefficient of friction. So to find the total force of friction, you have to do coefficient times Fn. There's two types of coefficients. You've got mu s, so that is your static friction. That's if the object is not moving. And you've got mu k for if it is moving. Mu s is typically greater than mu k. Now when the object is still, your force of friction is actually kind of variable. So your force of friction, when it's static, has a max value, we'll do a max, of mu static times Fn. But that doesn't happen all of the time. Like, you can't just set an object down and say that the static friction pushes it backwards if that's the only horizontal force. Like if this was your free body diagram, you had Fn and this was Ff, and you weren't pulling it at all, and it's just sitting there, the friction's not going to cause it to go. Friction resists motion. So actually the friction, it increases with a force applied. So if a force applied shows up, force of friction matches it, like so, until that force applied is greater than the force of static friction. So that's the maximum force of static friction. And if the Fa overcomes that, it starts moving, it becomes kinetic friction. So to find the amount of force required to overcome that, you'll do your sum of forces equals whatever Fa minus force of friction max. And then if you're on a ramp, there might be another force there, like mg sine theta or whatever you've got. And to find the amount of force you have to apply to overcome that static friction, you do ma, okay? And the a there equals 0 because it's right on the cusp. It's right at the verge of where you're going to start moving, okay? I'm assuming you guys already know how to do that. If you don't and you need a full video on it, feel free to ask me, or I'll find one and link it to the Google Classroom. But the big deal today is going to be terminal velocity, so let's move on to that. So terminal velocity applies to objects that are moving through a fluid. Now, fluids can be defined as liquids or gases, so moving through the air counts as well. Okay, like a skydiver falling down and reaching terminal velocity is moving through the fluid of a gas. Okay, gases count as fluids. It's kind of weird. But the deal is that the fluid resistance, okay, that's kind of like friction from the fluid. The fluid's not a surface to slide across, but the air resistance is the same thing as fluid resistance. It's a type of friction. So the fluid resistance is velocity dependent. Okay, the faster you're going, the more resistant it is. Okay, so the faster you're falling, the more you feel the air resistance. And it's also dependent on the fluid as well. So we're gonna have to take both of those into account. Now the part about velocity, it being dependent on velocity, is dependent on the v. The fluid dependency is quantified as a k. That is a constant for fluid resistance. And much like the mu we just talked about, it's also dependent on the object. So more aerodynamic objects have less fluid resistance, and then less aerodynamic objects have more fluid resistance. So it's dependent on both the fluid itself and on the object. Okay, so both of those things are taken into account with your K constant. It's a constant of proportionality. However, there's actually going to be two different equations that we can use for fluid resistance, kind of depending on the situation. So this can also be a capital D for a different equation. Okay, it can be a K or a capital D. So there are actually two cases that we're going to be looking at with terminal velocity today. The first one is represented with this equation. It's F, that's the resistive force, the fluid resistance, or the frictional force, whatever you want to call it, but that is a force. And it equals K, that's that constant we were just talking about, times the velocity of the object. So K is a constant, V is the velocity. Now this case only applies if the object is going at low speed. There's a second case that says the force is the same, equals D, that's the constant for this equation, times velocity squared. Okay, so over the course of the fall, as the speed changes, it actually is modeled better by this equation, and this happens at high speed. And usually this top one is called resistance, like air resistance, and then this bottom one is called drag, air drag. So let's go look at this in a free body diagram. So for this example, we're going to think about, the book has an example of a metal ball falling through oil, and we're going to show the forces on it. So the one force we got is mg, which is the force of gravity. And then you've also got frictional force going up, so that's little f. So if we wanted to write the sum of forces, it would be, and let's go ahead and make positive down. Down's positive, up is negative. I like it that way for this. So that's going to be mg minus little f in the I hat direction. And we can say that that equals our mass times acceleration. But we can actually do a little bit of substitution, and I'm going to go ahead and kind of move everything over so I got some more space. We can do some substitution here. We've got mg minus, and we're going to say this is case one, where the object is moving slowly, we're not at high speeds. So we're going to do minus k times velocity, and that is velocity specifically in the y direction, so we can leave it in here with the I. And I'm actually going to change that to say y, so it doesn't look quite so much like initial velocity, because that's not what I want. There we go. And that has equal mass times acceleration. So now we need to kind of figure out what's happening to this motion. So we can go ahead and drop the I hat and assume that the acceleration is also going to be in the I hat direction. And we'll just look at everything from there. So we've got mg minus kvy equals mass times acceleration, everything here happening in the y direction. But we know that acceleration equals the derivative of the velocity. So you've got mg minus kvy equals m dv dt. And in order to manipulate that equation, I'm actually going to take it to a new slide. So our goal here is to find the terminal velocity. In order to find the terminal velocity, and we're also going to need to figure out what motion is happening. But in order to find the terminal velocity, we got to impose a condition on this. And the condition is that at the terminal velocity, the acceleration is 0, because the velocity is not changing anymore. So that's going to make this equal 0. So we'll have mg minus kvy equals 0. So that means at terminal velocity, and you can solve this, I'm changing it to vt because that's terminal, equals mg over k. So that guy's pretty easy. That's terminal velocity. Woo. No calculus involved. But we care not only about the terminal velocity, we care about the motion itself. So we're going to hang on to the terminal velocity really quick. I'm going to erase that stuff I don't need. And we're going to solve this sucker for the y motion. And really at this point I'm just doing it because it's cool. If you don't want to do it, just skip forward a little bit till I start doing the graphs. So in order to solve this, we're going to have to do a little algebraic wizardry. So the first thing I'm going to need is this Vy kind of multiplied by everything else on this side. So in order to do that, we're going to divide everything by k. So you get mg over k minus Vy equals m over k dv dt. And what you might notice here is that this guy right there is our terminal velocity. So we can rewrite that as Vt minus Vy, and Vt is a constant, equals m over k dv dt. So now we're going to do what's called a separation of variables. It is a sorry, I can't write and speak at the same time. Separation of variables is a differential equations technique. You might have learned it in calculus before, but essentially what we need to do is get all of the times on one side and all the velocities on the other so we can find the velocity as a function of time. And in order to do that, we can actually split up this derivative exactly like you would split a fraction. Okay, so we're going to multiply by dt on both sides, and you get dt times Vt minus Vy equals m over k dv. But then we need to get all the velocities on the other side, so we end up with, I'm going to go ahead and split this as k over m dt equals dv over Vt minus Vy. And then I'm going to take that to the next slide, that way I can solve it. Now the book actually has this slightly differently. It has this multiplied all by -1, so I'm going to do that for consistency. That becomes negative, so those two switch, and we end up with negative k over m dt equals dv over Vy minus Vt. And that's what they've got. So that's what I'm going to stick with, even though it is a little bit different than what we just got. All we did was multiply everything by -1. So from there we got to integrate. The integral of negative k over m dt is negative k over mt. But this one's trickier because you've got dv over the Vy. I'm going to leave out the Vt for a second. You can see the integral of that. It's like du over u. So that is going to be a natural log. Ends up being the natural log of, let me think here, Vy. Oh, nope, it ends up being negative. V minus Vy over Vt. And then from there, we've got to rearrange everything. We're solving this for Vy. So to get rid of that natural log, we got to do e to the x, so it's e to the negative k over mt equals Vt minus Vy over Vt. So we can multiply both sides by Vt, and then we'll have to move everything around, flip that to this side, take the negative Vy over there, and you get Vy equals Vt minus Vt e to the negative k over mt. Factor that out, you get Vy equals terminal velocity times 1 minus e to the negative k over mt. So you can see it's not a very pretty function. Now if you want to see the y function or the acceleration function, you can integrate or differentiate that as necessary. I'm not going to keep going on it here. It shows you the answers to those in the book. You're welcome to complete those if you like. Now terminal velocity for case 2 is really easy to solve, and we're not going to go into that much detail. For case 2, the equation was the friction equals drag coefficient times v squared. So our free body diagram ends up being mg going down, friction headed up. So it's mg minus F, if I make this positive and that negative. And if it's terminal velocity, our acceleration is 0, so it equals 0. So you've got mg minus dv squared equals 0. Solving that for v, you got to move mg equal to dv squared divided by d. Those cancel out. To get v, take the square root. So you get velocity equals square root of mg over d for a high velocity case. Not going to do all the differential equations on that because our separation of variables would not be enough. But you do kind of need to vaguely know how the graphs would look for this. So we'll have a position time, so it's y, a velocity time, velocity, and an acceleration time. And these are shown probably in a lot better drawings on page 147 of the textbook. So if there was no fluid resistance, if it was a straight up falling, our acceleration graph would look like that, okay? Constant acceleration. So our velocity graph would look like so, constant velocity accelerating. And then our position versus time graph would be parabolic, like so. Though that's what it would be normally with no resistance. But in red, I'm going to draw what it does look like with resistance. And these are more accurate for case 1. But over time, our acceleration kind of evens out. It asymptotically approaches 0. Okay, so we're going to get to that terminal velocity where acceleration is 0. It's declining over time, which means our velocity, it's increasing, but it slowly lines out to stop increasing. Okay, it's going to end up asymptotically hitting that terminal velocity, Vt. This asymptotically approaches 0. And then our y position, assuming down is positive, ends up parabolic, or starts off kind of more parabolic, but ends up being a more straight line, constant, like so. So that's kind of what those graphs look like. You should be able to sketch them or recognize them when you see them. But you don't really need to find the specific equations for each. All right, well, that's all I've got for you on terminal velocity. The nitty-gritty of that second case, finding the acceleration and the y function, is a little bit beyond our grasp as far as the math goes. But you do need to know how to find those terminal velocities using the condition that the force of gravity equals the force of friction. And you need to know kind of what these graphs look like. So that gives you some questions to go try. Let me know if you need anything, and I'll see you next time.